We are now going to do a type of problem that is essentially the inverse of the type of problems we did in the previous screencast. Here's the scenario. Mensa is a social group for people with high intelligence. Suppose it requires its members to be in the top 2% of IQ among adults in order to be admitted. What's the lowest IQ a person can have and still be admitted to Mensa? Recall that IQ distributes normally in the adult population and has a population mean of 100 and a standard deviation of 15. So before we even get into understanding how this is essentially the inverse type of problem of what we've done previously, let's just first get a picture of what's going on here. We've got IQ score, which distributes normally. The mean is 100. This is a pretty ugly looking bell curve, but you get the idea. This value right here would be 115, one standard deviation to the right, which puts you at the inflection point. It's 115. And ultimately, our question here is what's the lowest IQ a person can have and be admitted to Mensa under the condition that you have to be in the top 2%. Top 2% means we are concerned with this area out here being exactly 2% or 0.02. We want to find what's the minimum. All of these people over here, their IQs, they get admitted into Mensa. The minimum is right here. We're concerned with what's that minimum value for which you could still be admitted into Mensa. Now, the reason that this is essentially the inverse type of problem from what we did previously is we now have the area or the probability. We're starting with that. And ultimately, we want to work back to this particular value here, which is an x value. So in the previous screencast, we went from an x to a z to a p. In this one, we start with the p, we go to the z, and then we have to convert back to the x. Let's go from the probability or the area to the z-score first. So we're going to go from p to z. We need to have an area of 0.02, but we need the area to be 0.02 to the right. So since our table has area to the left, we need to convert this to a problem with area to the left. This raw data value has 0.02 of the area to the right. So how much does it have to the left? Well, that would be the rest. If 0.02 is to the right, then 0.98 is to the left, since the total has to be 1. So this area 0.98 is what I'm going to look up in my table. So over here, you've got the standard normal distribution table. And with the previous types of problems, you started with a z value, then found the probability or area. Here we're going backwards. We're starting with a probability or an area. So we're going to work from the inside of the table. Then we're going to work out to the corresponding z-score. That's what we're doing. We're going from the probability to the z-score first. So what we need to do is find 0.98 in the heart of the table, or whichever number is closest to 0.98. And if you go through here, right down here, 0.98 would be between 0.9798 and 0.9803. But 0.9798 is the closer one. So I'm going to circle that really quickly. So we're approximating this as 0.98 is approximately the 0.9798. So we found the area in the table. We now want to look and see what that corresponding z-score is. And you'll notice it's 2.05. So we have a probability of 0.98. We converted that to a z-score of 2.05. Now we need to go to the final step from z to x. And to get from z back to the raw data value x, we need to use the z-score formula. But instead of using the z-score formula in this form, we can multiply both sides of this equation by sigma and then add mu to both sides, and we get an equivalent equation that has the raw data value x isolated. So this z-score formula is exactly the same thing as this one. Just in this z-score formula, the z is isolated. In this z-score formula, the raw data value x is isolated. So we're going to use this when we try to go from z to x. Our raw data value, which is where we want to end up, is equal to mu, well, the average score was 100, plus the z-score we just found was 2.05, and sigma is 15. This will now give us the lowest possible score for which you could still be admitted to the social group known as Mensa. And if you do the arithmetic, we get x equals 100 plus 2.05 times 15 is 30.75. And then if you add these two, x is equal to 130.75. Now, I don't believe IQ is ever measured with decimals, but we can leave it like this. So essentially, you need to have an IQ score of at least 130.75 to get admitted into Mensa. It could certainly be higher, but it can't be lower to meet the criteria that you have to be in the top 2% of IQ. So again, we essentially did the opposite of what we did in the previous problems. In the previous problems, we had X values and we wanted to get P values. We had to go to Z in between. Now we're given P values or areas and we want to get to X values and we still have to go to Z in between. Let's take a look at another problem. A stat teacher found that the actual time studying for the last test was normally distributed with a mean of 8.1 hours and a standard deviation of 2.2 hours. The teacher is concerned about the progress of the students in the lowest 5% of these times and wants to develop a study plan. What is the study time she should be looking for as the cutoff? So I'm going to start with a picture here, and I highly recommend that you use pictures to solve these problems. Study times distributed normally according to this stat teacher with a mean of 8.1 hours. And we want to know what's the cutoff score for the lowest 5% of studiers. So the lowest 5% means we want this tail over here to have an area of 5%, which of course is 0.05. So we want to find this study time, which is the cutoff for this low end of studiers, the lowest 5% of studiers. To do that, again, our strategy is to take that area or that probability, which is the 0.05, convert it to a z-score, and then convert that to a raw data value x. Well, we are given a probability. This is not a z-score of 0.05, this is a probability. So we're not looking out here. We are looking in the heart of the table for a probability of 0.05 or whatever is the closest. And you'll see that down here, 0.05 is halfway between both of these. Technically, we could take the average of those two z-scores associated with that, or you can just pick one. It doesn't matter to me. Let's just say we'll pick this one right here. 0.0495 is our approximation of the 0.05. So the corresponding z-score that we're interested in, which has 5% of the area to the left, is z equals negative 1.65. So 5% of the area under the standard or normal distribution curve is to the left of negative 1.65. Now we need to go the extra step of converting that z-score back to the raw data value. And we're going to use our z-score formula here. So we've got x equals mu, which is 8.1, it's given to us, plus z, we just found is negative 1.65, times sigma, which was given to us as 2.2. And if you do this arithmetic, we get x equals 4.47 hours. So this stat teacher wants to target an intervention for any students that study for 4.47 hours or less. That would put them in the bottom 5% of study times.